Welcome to Lecture 8. Today we will start with the next focus, which is aldehydes and ketones. But before we start, we will shortly revise the last lecture. Last lecture, we concentrated on the reactivity of substituted benzenes and on the synthesis of substituted benzenes. And for the reactivity of substituted benzenes, we learned that substituents with plus I or plus M effect are activating groups, as they are electron donating, and hence these groups increase the reactivity of the ring to reactions with electrophiles because the carbocation is stabilized by the electron donating group. And what was also important is that we know that the plus M effect is stronger compared to the plus I effect. Hence, electron donating groups with plus M effect stabilize the intermediate carbocation better compared to substituents with plus I effect. Conversely, we also saw that groups with minus I or minus M effect, so electron withdrawing groups, are deactivating groups. And the reason for this is that electron withdrawing groups destabilize the intermediate carbocation and hence decrease the reactivity of the ring with electrophiles. And again, the minus M effect is stronger compared to the minus I effect. Hence, groups with the minus M effect destabilize the carbocation stronger than those with minus I effect. Moreover, we learned that activating groups are so-called 2,4 directing activators. And if the activating group is larger, then steric effects become more important. That means for larger substituents, the position 4 on the ring is preferred. Conversely, deactivating groups are so-called 3 directing deactivators. Then we also learned that halogenes constitute an exception. If you have a halogenobenzene, the halogene has a minus I effect because of the high electronegativity. Hence, it is a deactivating group. However, the halogene has also a plus M effect, which is, however, weaker than the minus I effect. But this weak plus M effect directs the electrophile to the 2 and 4 position of the ring, as hereby the intermediate carbocations have an additional resonance form and are therefore better stabilized. And this additional resonance form results from the delocalization of the lone pair of the halogen atom over the ring. Hence, the halogen substituents are 2,4 directing deactivators. And here we have an overview about all substituents which are important for us with the corresponding effects. After the reactivity of substituted benzenes, we also discussed the synthesis of substituted benzenes, and we learned that most of the time only one structural isomer is required, which can be difficult to achieve. Therefore, it is important to take these questions into account. So the first question is the substituent an activator or deactivator? And then, does the substituent direct the electrophile in the 2 and 4 or in 3 position? Another question is, how reactive is the electrophile? What are the reaction conditions? Moreover, we should ask, are there any byproducts formed? And does the product react further? And then we learned that only a limited range of electrophiles react with benzene in electrophilic substitution reactions. Accordingly, it is helpful to transform existing substituents into other functional groups. And such transformations can, for example, be done by a redox reaction. So that means by a reduction or oxidation. And hereby, it is possible to transform a deactivating substituent into an activating substituent or the other way around. And here we can see some examples. So for example, if we start with benzene and we perform a halogenation, then we introduce a 2,4 directing deactivator as substituent. Conversely, if we perform a sulfonation, we will introduce a 3 directing deactivator. If we perform a Friedel-Crafts acylation, we end up with also a 3 directing deactivator. If we then make a transformation by a reduction, we end up with a 2,4 directing activator. Conversely, if we perform a Friedel-Crafts alkylation, we first induce a 2,4 directing activator, and then later on we can transform it into a 3 directing deactivator. And similar for the nitration, we first introduce a 3 directing deactivator, which can be then transformed into a 2,4 directing activator. So this is a way how to use the substituents in order to transform it into another. And then we learned that a wide range of substituents can also be introduced based on the reaction of an aryl diazonium ion. And here we can see an overview about all these possible reactions. So the 3 with the copper 1 salts are the so-called Sandmeyer reaction. And then you can see that we have further possibilities in order to introduce a substituent. And also important for the synthesis of substituted benzenes is the order of the substitution. We need to consider which substituent should be introduced first in order to achieve the desired product. And if the substitution yields a mixture of different structural isomers, then we can easily separate those, for example, by distillation, as structural isomers have different physical properties. Another approach for synthesizing substituted benzenes is the use of temporary substituents, which are also called blocking groups. As we now know, an activating group directs the electrophile to the position 2 and 4 on the benzene ring. And the ratio of the formed structural isomers depends on the size of the activating group. And the larger the activating group, the greater the amount of the 1,4 substituted structural isomer. And for small activating groups, a relatively large amount of 1,2 substituted benzenes will result, which can be a problem if the 1,4 substituted benzene is required. So to increase the selectivity for the attack of the electrophile in position 4 of benzene, the size of the activating group is temporarily increased by transforming the substituent into a so-called blocking group. Then the desired substitution can selectively be performed. And then in the last step, the blocking group is then removed or back transformed into the initial substituent. This is what we learned about the reactivity of substituted benzenes and synthesis of substituted benzenes. And now we start with our third focus, aldehydes and ketones. And we will start with the structure of aldehydes and ketones. Both aldehydes and ketones contain a carbonyl group, so a carbon-oxygen double bond. And if we have a look on the general formula of an aldehyde, we can see it here. An aldehyde has at least one hydrogen atom connected to the carbon-oxygen double bond. Conversely, a ketone has 2 aryl or alkyl groups next to the carbon-oxygen bond. And the carbon-oxygen bond contains one strong sigma bond and one weaker pi bond, and the double bond is then formed by the overlap of the orbitals of a sp2 hybridized carbon atom and the sp2 hybridized oxygen atom. The sigma bond is formed by end-on overlap of a sp2 hybrid orbital of carbon with a sp2 hybrid orbital of oxygen, while the pi bond is formed by side-on overlap of an unhybridized p orbital of carbon with an unhybridized p orbital of oxygen. And each of the 2 remaining sp2 orbitals of oxygen contain a lone pair of electrons, while the 2 remaining sp2 orbitals of carbon form 2 further sigma bonds. And if we have a look here, all 3 sigma bonds of carbon are in the same plane and form an angle of 120 degrees to each other. And important to know is that the carbon-oxygen double bond is short and relatively strong, so it is stronger than the carbon-carbon double bond. Nevertheless, the carbon-oxygen double bond is reactive because the electrons in the carbon-oxygen double bond are polarized. And this polarization results from the difference in the electronegativity. So we know that the oxygen atom has a higher electronegativity compared to the carbon atom. And hence, electrons are attracted towards the oxygen. And therefore, the carbon atom is partially positively charged, while the oxygen atom gets partially negatively charged. And therefore, nucleophiles will attack this carbon atom, while the partially negatively charged oxygen atom will react with electrophiles. Also important to see is that we can draw a resonance form of the carbonyl group. So we can either draw it like this, so as uncharged molecule, we just have a partial charge on the carbon and the oxygen atom, but we can also draw the resonance form with positive charge on the carbon atom and a negative charge on the oxygen atom.